Hi everyone, I'm Prateek Jain. I'm a PhD student at Boston University, and today I will be discussing our paper titled Design and Modeling of a New File Transfer Architecture to Reduce Undetected Errors Evaluated in the Fabric Test Framework. Scientific instruments today, like those used in physics, astronomy, and healthcare, generate petabytes of data. In such massive datasets, even a single error can lead to completely wrong conclusions. When the goal is to detect rare or critical events, these wrong conclusions could be fatal. Traditionally, we have two checks on internet. One is a CRC, which is a 32-bit hop-to-hop check at data link layer, and the other one is internet checksum, which is a 16-bit end-to-end check at transport layer. Errors in the network can be because of transmission errors or memory access or hardware issues. Statistically, CRC is supposed to miss 1 in 4 billion errors, but practically, errors missed by both CRC and TCP combined is much higher. This is because errors arising from hardware issues or memory access might not be detected by CRC. Our focus in this paper is on the errors that arise from transmission or hardware issues or in the intermediate system or at the source or at the destination. We consider even a single bit error in the final transmitted file will render the file useless, requiring a retransmission. There are many frameworks which provide the functionality of additional error checks over the traditional checks during file transfer. Some provide an end-to-end chunk level check. If this check fails, then that particular chunk has to be retransmitted. Some other frameworks provide an end-to-end file level check. If this check fails, then the whole file has to be retransmitted. As you can notice, some of the frameworks provide both of these checks, showcasing a multi-level error detection. But these frameworks do not utilize network resources and have other limitations that we will try to address with MLET. We propose MLET, that stands for Multi-Level Error Detection Architecture. MLET is a recursive error detection framework which utilizes in-network resources to reduce undetected error probability in large-scale file transfers. MLET is defined as MLET NP, where N represents the number of levels in the architecture. Each level I has a set of layers, and each layer has its own scope over which a layer-specific policy acts. The set of all policies for all the layers is defined as P in MLED NP. These layer-specific policies could be error detection, routing, congestion control, etc. They can potentially be different for different layers, bringing modularity and flexibility in MLED. Now to transfer a file from a source, that is node 1 here, to the destination, that is node 5 in the slide, we deploy MLET processes on source and the destination along with some intermediate nodes. These processes do IPC with each other and perform various checks on different size of chunks of data. Now for experiments, we wanted to compare MLET approach with the traditional approach with two checks. At level 1, we wanted hop-to-hop CRC, and at level 2, we wanted 16-bit end-to-end checksum, TCP checksum. We implemented the traditional approach in MLET architecture to ensure that packets go through the same path and face the same delays as in the MLET approach. Also, it makes it easier to control the errors in both the approaches. To show that there is improvement in MLET approach over the traditional approach, we augment the previous traditional approach with an additional level. That is, we add a simple 8-bit CRC check between CRC and TCP checksum levels of the previous setup, so that we can see if the errors missed by the traditional approach are detected by the MLET approach at the additional level or not. For experiments, we run both the traditional and the MLET setup on Fabric test beds such that each node is mapped to one Fabric VM following the path from Chicago, which is the source, to New York, Washington, D.C., and Atlanta, which are the intermediate nodes, to Dallas, which will be the destination in our case. To make sure that both the traditional and the MLET approaches face the same errors for fair results, we use an adversarial error model to introduce errors. The introduced errors make sure that they are missed by traditional checks, rendering the final file corrupt, requiring retransmission of the entire file in the case of traditional approach, therefore doubling the file transmission time in this case. We can see that the time taken to deliver the file in both 10 GB and 20 GB case is half in case of MLET approach compared to the traditional approach. This shows that all the errors that were missed by the traditional approach are actually caught by the additional level in case of MLET approach. You can learn more about MLET by scanning this QR code. Thank you.